Hello friends, welcome to YouTube channel Electronics. In this video, we will learn how to design an astable multivibrator using 555 timer IC. In this mode, the IC becomes an oscillator or free running multivibrator. It will continuously pulse until power is removed. Astable multivibrators can be used to flash lights and buzzers on and off repeatedly. In previous video, we have discussed 555 timer IC working and internal construction in details. We have discussed that by altering the voltage levels at threshold and trigger pins below or above the reference voltages of 2/3 and 1/3 VCC levels, we can alter the output voltage level. The 555 timer IC has three operating modes: astable, bistable and monostable. Let's see how the 555 timer works in an astable mode. So here is the circuit of 555 timer IC configured as an astable multivibrator. In this configuration, the IC becomes an oscillator. So its output continuously switches between high and low without application of any external trigger signal. Let's see how to design the astable multivibrator using the 555 timer IC. Just take two resistors and one capacitor. Connect them in series as shown here. Connect the capacitor end to ground and connect the resistors end to VCC. Next, connect discharge pin 7 to the junction point between R1 and R2. Next, interconnect threshold pin 6 and trigger pin 2. Connect this to the junction point of resistor and capacitor. We don't use reset function, so connect reset pin 4 to VCC. We don't use control function, so connect pin 5 with a 10 nanofarad capacitor to the ground. Now when the power is switched on, the output of the circuit continuously switches between logic low state to logic high state. So it behaves like a free running multivibrator. The time period of the pulses is given by the expression T equals to 0.693 into R1 plus 2R2 into C1. Now let's see how this circuit produces continuous pulses. Initially this capacitor is uncharged. So whenever we turn on this circuit, this uncharged capacitor acts as a short circuit. Hence the voltage at this pin number 2 and 6 will be equals to 0 volts. As we know that the voltage at these two nodes of the voltage divider will be equal to 2/3 VCC and 1/3 VCC respectively. Here these voltage levels are the inputs of these two comparators, and as per comparator's logic, the first comparator inverting input is greater than non-inverting input, so it gives a logic low level output, while the second comparator non-inverting input is greater than inverting input, so it gives output of logic high level. If we observe over here, the next is RS flip-flop. Here R input becomes logic low level and S input becomes logic high level. So according to RS flip-flop truth table, the Q output becomes logic high and Q bar output becomes logic low. As we know that the output stage is an inverter stage, and because of that the output of the 555 timer will becomes logic high level. Here this discharge transistor will get low level at its base, so it will be in off condition. Hence the VCC voltage cannot discharge through this transistor, so the entire VCC will appear across this capacitor and the capacitor starts charging, and the voltage levels at this trigger and the threshold pins will change. After some charging process, this capacitor voltage becomes greater than 1/3 VCC but lesser than 2/3 VCC. So the second comparator input levels will change. Here the inverting input will be greater than non-inverting input, so we will get low level at second comparator output. But according to RS flip-flop truth table, whenever both inputs are 0, there is no change in output. So we won't get any change in 555 timer output. We will still get high level at the output. Here this capacitor keeps on charging, and after some time this capacitor voltage is greater than both these reference voltages of 1/3 and 2/3 VCC levels. So the first comparator input levels will also change. Here inverting input becomes logic 1 and non-inverting input becomes logic 0. Hence first comparator output becomes logic 1. Here the next stage RS flip-flops input levels has changed. According to the truth table, if S is 0 and R is 1, then RS flip-flops Q becomes 0 and Q bar becomes 1. Because of this, now the 555 timer IC final output level will changes from logic 1 to logic 0. This transition in the output from logic high value to logic low value can be represented like this. If we represent this output transition in a graph, whenever the capacitor voltage level is in between 1/3 VCC and 2/3 VCC level, then the 555 timer output will be in logic high level. And whenever the capacitor voltage is greater than both 1/3 and 2/3 VCC levels, then the 555 timer output level changes from logic high level to logic low level. So now this discharge transistor's base terminal will get logic high level. Hence this transistor turns on. So it acts as a closed switch. Due to this, the entire VCC will drops across this resistor R1. And once this transistor becomes on, this capacitor will start discharging through this discharge terminal. And gradually the voltage stored in this capacitor will start reducing. And as soon as this voltage level comes in between these reference voltage levels of 1/3 and 2/3 VCC levels, then the first comparator input status will change. Threshold input changes to logic 0 and 2/3 VCC level becomes logic 1. Hence the first comparator output will becomes logic 0. But the second comparator remains 0 because there is no change in their input state. So according to RS flip-flops truth table, if both inputs are 0, then output will not change. Here output Q bar remains logic 1 state and 555 timer output will also remains in its previous state of logic 0. This capacitor keeps on discharging, and whenever the voltage across the capacitor is less than both reference voltages of 1/3 and 2/3 VCC levels, the second comparator input levels also changes. Trigger input goes low, and because 1/3 VCC is greater than trigger input, the non-inverting input becomes logic high state. Now the second comparator output changes from logic low state to logic high state because its non-inverting input is greater than inverting input. In next RS flip-flop stage, its input logic states have changed. So according to RS flip-flop truth table, whenever set input is logic 1 and reset input is logic 0, then its Q output becomes logic 1 and Q bar output becomes logic 0. Hence the 555 timer IC output also changes from logic low state to logic high state. Here we will see a transition in the output from logic low state to logic high state in the timing diagram. Now this discharge transistor will get low level at its base terminal because here Q bar is 0, so it becomes off. Hence this capacitor doesn't have discharge path and it will again start charging through resistors R1 and R2. So in this way this capacitor is charging through resistors R1 and R2, but it discharging through only resistor R2 above and below the reference voltages of 1/3 and 2/3 VCC levels. And because of the charging and discharging of this capacitor, we will see a transition in the output level of the 555 timer IC. So initially the 555 timer IC output stays in logic high state, and during capacitor charging process, whenever the voltage across the capacitor just crosses 2/3 reference voltage, then there is a transition in the output from logic high state to logic low state. And likewise, during capacitor discharging process, whenever the voltage across the capacitor just goes below 1/3 reference voltage, then there is a transition in the output from logic low state to logic high state. And if we see this in a timing diagram, here VCC 2/3 and 1/3 VCC levels were represented in a dotted lines, and we will represent output of the 555 timer in blue line and charging and discharging of the capacitor in green line. So initially, whenever the circuit is just turned on, at that time the output of the 555 timer will be high and the capacitor will start charging towards the VCC voltage. As soon as the voltage across the capacitor reaches at 2/3 VCC voltage level, then we will see a transition in the output from logic high value to logic low value, and now the capacitor will start discharging towards the 0 volt. And as soon as voltage across the capacitor reaches the 1/3 VCC level, then once again we will see the transition from logic low value to logic high value. In this way, the capacitor is charging and discharging between 1/3 and 2/3 VCC voltage levels, and we will get transition in the output of the 555 timer from logic high value to logic low value. So here T1 is the time for which the output of the timer is logic high state, while T2 is the time for which the output of the timer is logic low state. Or we can say that T1 is the charging time of the capacitor, while T2 is the discharging time of the capacitor. So if we represent this T1 and T2 mathematically, T1 equals to 0.693 times R1 plus R2 into C, while T2 equals to 0.693 times R2 into C. Here we can see that T1 is greater than T2. It is because during the charging process, the capacitor is charging through resistor R1 and R2, while during the discharging process, the capacitor is discharging through the resistor R2 only. And that is why T1 will be always more than T2. Here we can say that the duty cycle of this stable multivibrator will be always more than 50%. Now over here, the total time period T will be equals to T1 plus T2. We can write this like here. So if you simplify this equation, T equals to 0.693 times R1 plus 2 R2 into C, and the duty cycle can be represented as on time T1 divided by total time period T. So the duty cycle can be written as 0.693 times R1 plus R2 into C divided by 0.693 times R1 plus 2 R2 into C. Here we can cancel out these 0.693 and C. That means the duty cycle will be equals to R1 plus R2 divided by R1 plus 2 R2. Here we can say that for this particular circuit, the duty cycle will be always more than 50%. Suppose if we make this R1 value equals to 0, then duty cycle will be equals to R2 divided by 2 R2, that equals to 1 by 2, that is 50%. So in this circuit, whenever the resistance value of R1 is equals to 0, at that time we can achieve a 50% of duty cycle. But whenever this R1 is equals to 0, at that time the entire VCC voltage will appear at the collector of this discharge transistor, and whenever this transistor is on, at that time it will draw maximum current. Because of this, the internal discharge transistor may get damaged. So we cannot use this method for to get 50% of duty cycle. Hence we must use any other alternative method to achieve the 50% duty cycle. If we connect a diode in parallel with resistor R2, we can achieve 50% duty cycle or even lesser than 50% duty cycle. So let's let's see the working of this circuit. During the charging process of this capacitor, this diode D will becomes on. Let's say the diode's forward resistance as RD. As we know that the forward resistance RD is less than this R2. So during the charging process of this capacitor, it will charge through resistor R1 and diode D. So we can write charging time T1 equals to 0.693 times R1 plus RD into C. Here RD denotes diode's forward resistance. But during discharging process of this capacitor, this diode becomes reverse biased. So it cannot discharge through this diode. Hence it discharges through this resistor R2. So the discharging time T2 equals to 0.693 times R2 into C. Now if we observe these both equations, we will find difference here. If we adjust the values of R1 and R2 in such a way that R1 plus RD equals to R2, then both these equations T1 equals to T2, that is on time and off time are becomes equal. So we can achieve 50% of duty cycle. To make R1 plus RD equals to R2, we can use a variable resistor in place of R1. Suppose if we assume that this diode is an ideal diode, then the diode's forward resistance RD will be equals to 0. In that case, we must make this R1 equals to R2. So in that case, we will use equal value of resistors for both R1 and R2. Here we will use equal value resistors R instead of both R1 and R2. Now this capacitor charging through this path and the total resistance equals to R, and it is discharging through this path. Here also the total resistance is R. So here T1 equals to 0.693 into R into C and T2 equals to 0.693 into R into C. Both on time T1 and off time T2 are same. So the total time period T equals to 2 times 0.693 into R into C. Now duty cycle equals to T1 by T. So that equals to 0.693 into R into C divided by 2 times 0.693 into R into C. Here we can cancel out these two terms. Hence our duty cycle will be 1 by 2. That equals to 50%. So by using an ideal diode and two equal value resistors, we can achieve 50% duty cycle at the output of the 555 timer IC. If we observe the timing diagram, it will be an exact square wave because the on time and off time of the 555 timer IC is same. And even by using this circuit, it is even possible to achieve either more or less than the 50% duty cycle. So if we adjust both these resistors R1 and R2 in such a way that R1 is greater than R2, then we will get more than 50% of duty cycle. Likewise, if R2 is greater than R1, then we will get less than 50% of duty cycle. So using this circuit, it is possible to achieve the desired duty cycle. Just remember, duty cycle equals to R1 divided by R1 plus R2. So now let's try to design a stable multivibrator circuit whose frequency f equals to 1 kHz and the duty cycle is equal to 40%. Here the duty cycle is less than 50%. So to get a duty cycle of 40%, the value of resistor R1 must be lesser than R2. Duty cycle equals to T1 by T. That equals to R1 by R1 plus R2. Here our duty cycle is 40%. So 40% equals to R1 by R1 plus R2. If we multiply both these terms, then 0.4 R1 plus 0 0.4 R2 equals to R1. We take this to right side. Then 0.4 R2 equals to R1 minus 0.4 R1. That means 0.4 R2 equals to 0.6 R1. If you do the division here, then R2 equals to 1.5 R1. This is our first equation. Next, here frequency f equals to 1 kilohertz. So the total time period equals to 1 by f. That equals to 1 millisecond. As we know that the total time period T of this 555 timer stable multivibrator circuit equals to 0.693 into R1 plus R2 into C. So here 1 millisecond equals to 0.693 into R1 plus R2 into C. Let's assume capacitance value of this capacitor is 0.1 microfarad. Let's insert this C value in this time period formula. Then 1 millisecond equals to 0.693 into R1 plus R2 into 0.1 microfarad. Let's simplify this equation. R1 plus R2 equals to 1 millisecond divided by 0.693 into 0.1 microfarad. After doing division, we will get R1 plus R2 value as 14,430. So here we got two equations. R2 equals to 1.5 R1 and R1 plus R2 equals to 14,430. We can write first equation as 1.5 R1 minus R2 equals to 0. Now let's add both these equations. Here we can cancel out minus R2 and plus R2 from both equations. Now we will get the value as 2.5 R1 equals to 14,430. So R1 equals to 14,430 divided by 2.5. That equals to approximately 5.8 kilo ohm. If we insert this R1 value in any one of these above equations, we will also get R2 value equals to approximately 8.6 kilo ohms. So here we need to use resistors of 5.8 kilo ohms and 8.6 kilo ohms in place of R1 and R2 respectively, and capacitor value is 0.1 microfarad. Then we will get the output which have 40% duty cycle and 1 kilohertz frequency. This is how we can design desired value of a stable multivibrator circuit using 555 timer IC. We can also design a monostable multivibrator using 555 timer IC. A monostable multivibrator have only one state, logic high or logic low. When monostable circuit triggered externally, it changes its state for short duration and return back to its original state. When we close the switch S1, the output of the circuit changes to logic high state and holds there for specific time duration and changes back to its original state of logic low level. The time period of this circuit is given by the expression T equals to 1.1 into C1 into R1. So we can increase or decrease the time period by changing the values of R1 and C1. We can also design a bistable multivibrator circuit using 555 timer IC. A bistable multivibrator have two stable states, logic high and low. It stays on the same state until and unless an external trigger input is applied. When we turn on this circuit, initially the output is at logic low level. When we close the switch S2, the output of the circuit changes to logic low level to logic high level. The output stays at high level even after we release this switch S2. Now when we close the switch S1 for a momentary duration, the output switches back to logic low level. The output stays at the logic low state until and unless we can again close the switch S2. Hence this circuit have two stable states. So it is working like a bistable multivibrator. That's all about design and working of 555 timer stable multivibrator circuit. If you have learned from this video, please do mention them in the comment section below. Thanks for watching. If you like this video, please click the like button. Help others to learn by sharing this video. Please subscribe and turn on notifications for more such videos. Have a nice day.